Already, okay? Guys, assignment number 3 is still there. It's coming. Just plenty of time. If you can get a little bit started before the written test, that'll be nice. But if you got to rush up, maybe after that, it's even fine. Just get something done before the deadline. Written test, Thursday, right, during your lecture time. So there was a review session yesterday, about 1 hour. The recording quality could be a little bit better. I do apologize. It could be a little bit better, but next time I'll make it better. But still clear. You can check it out if you are interested. We did talk about some useful topics there. And makeup lectures also cover about ADT and stacks. You already know that. Just for today, there's no office hour at 3 p.m. I just need to help section N on their test. So if you want to speak to me, feel free to come tomorrow, 3 p.m., normal office hour, and so on. Any question about the course? All right, good. Recap. All right, so last time we basically dived very deep into the mathematical properties of binary tree. We'll still do a little bit today. I would like to do some mathematical induction today. It's a very natural way of justifying properties for binary tree. That's something we'll get into. Okay, you can look forward to it. But let's now do something. Let's just recap first, right? Shouldn't say too much just yet. All right, so don't forget, you got this exercise here about calculating the heights for the tree. I got Java code. I got tracing here. You can look at the solution video. It's also on your lecture site. Right? You can check it out. It's all there. And we talk about how you can compute recursively, for example, the size, and also search for some value. Okay, I want to highlight one thing here. When we talk about this particular tree, because if A here is not really the element we're looking for, we somehow have to recur on the left subtree and also the right subtree to see which one contains the element we're looking for. However, today, in the second half, we're going to learn something called binary search. But we're going to learn that in the linear version first on the array or sequence. And once you guys learn about the basics about binary search today, when we come back next Tuesday, I'm going to show you how you can draw the connection from performing binary search on linear collection like array versus how you can perform binary search on a binary search tree, right? So that's something I'll connect you to. That's something we'll see, right? That's kind of the dots you want to connect before the exam. And we talk about this page over here, right? I kind of build from scratch about the maximum number of nodes at each level. And just don't forget, levels start always from 0, all the way until the maximum depth from the bottom nodes there. And we also talk about how you can apply the geometrical sequence sum. And make sure you know that formula for also Thursday's test. And then, yeah, you can look at the detail, right? Nothing else to say. And then we spoke about the difference between complete versus full binary tree, right? You can look at the textual definition on the slides. And also I gave you guys some visual intuition about the difference between the two, especially this page over here. I think that one nicely summarizes the difference between the two. But of course, you're going to look at the definition. You got to go over in detail how the numbers are derived. I might ask you a question about it, okay, in the test or exam. And we talk about two bounds. Whenever we say we got different measures about the tree, right? Especially for binary tree. We got number of nodes, we got heights, and what we're going to continue today about number of internal nodes and also the number of external nodes. So these are the 4 basic measures about what a tree, how the tree can look like. And we spoke about 2 of them, right? So you can review. Given certain heights, what's the minimum versus the maximum number of nodes for that particular tree, right? We spoke about the minimum and also maximum case in general, right? You can look at the detail. The heights over here is especially important because every time you want to run recursion on the binary tree, the performance of the tree can range from log n as the most efficient case versus n, which is linear, right? That's something I'll draw a little bit more connection to once we learn about more basics, especially about binary search today. Okay, I'll get the more connection done maybe next Tuesday. But but make sure you review this about the different bounds before Thursday, right? It's going to be useful. All right, and then we spoke about pre-order and post-order. So pre-order and post-order, they have no precondition given any tree. Can be general tree or can be binary tree. You can always do pre-order or post-order traversal. So we talk about these two on the family tree. And also we spoke about this particular expression tree for pre-order and post-order. And the in-order traversal is the only thing I'm going to left out from last Thursday. I'm going to complete this example here in just 30 seconds or 1 minute, right? But you also got to make sure you know how to do in-order traversal. I'll get there once we get there, okay? A little bit later. So in order traversal, make sure you also can do. So the best way to do is to remember the principle. You can go back to the slides where I include some like a pseudocode-like Java code there to show to you what's the sequence of doing the recursive call. That's something you want to review before Thursday. All right, any question from last time? All right, if no, let's now talk about more mathematical property, namely internal nodes versus external nodes. Okay, so, right here. Okay, let's say do 2 more pages about the bounds. They are not too hard, right? It's just basically a continuation from last time. We're going to talk about what's the lower bound and upper bound for external nodes, first of all. And then, symmetrically, what about internal nodes? What about their bounds? So these are the 2 properties left. Okay, let's now talk about them. And if you remember the definition, external node is simply the nodes without any children, without any child nodes. Internal nodes are those nodes that has at least one child, which means when you run into some internal node of your tree, you may have to run further recursion for your algorithm. Okay, external nodes are usually the base cases, usually. Let's talk about external node first. And we'll start with some example. Let's say the height of the tree is 3. And let's just remind ourselves, what's really height? When you say the height is actually equal to 3, 3 here tells you the maximum number of edges from the bottom level to the root. The maximum number of edges from the bottom node to the root, right? That's a very definition for height or maximum depth, if you like. How do we visualize this tree in the minimum case? Well, in the minimum case, cannot be 0, because you must have at least one leaf in the tree if you think about it. So the minimum you can get is 1. How do I draw? Just with 1 external nodes. Let's say I start with just this node here, right? It's 1, and then I can go another one here. But if I go, for example, here, let's say, in this case, I somehow got 2 external nodes, right? So that may not be the minimum. I want to somehow make sure when I expand the number of nodes here until the height, I want to keep just 1 external node as much as possible, okay? So I'm going to undo this. So I got 1 edge right now. I got another edge. I got another edge right here. So this will be the case where you got just 1 external nodes. So you can see this one here is the only external nodes. External node. Whereas all the others are internal, obviously, right? So all the others, 3 nodes over here, are internal nodes. They are internal because you can see this one here has at least 1 child. This one has at least 1 child. And this one here has at least 1 child. And this one here has no child. Right? So that's a minimum case. Very easy to generalize. If I got just h in general, h can be arbitrarily large. Then the way to visualize that would be I got a root, start from that, for example. And then I can go just one, like a slanted tree, which we spoke about last time, right? So you can go all the way to the bottom over here. Okay, so let me visualize that a little bit better. Okay, right here. You can think about the last node here will be the external. All the rest will be internal. Okay, we can be even more precise about it. One moment, internal nodes. And then in this case, you can think about the maximum number of edges. So start from here. Start from the bottom node, go all the way to the root, right? That's kind of the ancestor path for the bottom external nodes. That one there should be exactly h. So the depth of this single external node is exactly h, right? So that's minimum case, just 1. So that's why you will see the number 1 here. All right, minimum case. Right? What about the maximum case, right? For the maximum case, you want to make the tree as flat as possible, not as high as possible. That's basically the opposite direction you're going. But let's see exactly how it can look like. Let's say if I got height to be 3 right here, right? I can still start with this slanted tree. I can start with that first. So I'm going to draw something like this. So let's say I start with the root, and then 1, 2, and 3. Right? So that's the minimum case. However, if I want to get more external nodes, I can just try to add more children along the way, so I can get more at the bottom level. That's the intuition. Right? How do we do that? Well, just expand as much as you can. Okay, 1 here, 1 here, 1 here, 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 and here. I'm basically making a full binary tree, in which case the bottom level there will have the maximum number of nodes for external, right? All right, so this case, you can see here, the number of external nodes, if you think about this, is depth 0, depth 1, depth 2, depth 3. That'll be 2 to the power of 3, right? We learned about this formula last time, 2 to the h, which will be exactly 8. So we got 1, 2, 3, 4, 5, 6, 7, 8. So these are all external nodes. So that's a maximum case you can get at the bottom. Okay. All right, so these are all the external nodes. How do we make it a little bit more general? Also very easy. So if you look at that, let's now draw the general case. The general case will be if you got the height of the tree being h. H can be arbitrary number. And it would be actually the maximum if the tree happened to be full. You can look at the definition for full binary tree. So this will be a full binary tree. And in which case, if you look at the bottom level here, so these nodes are all external, right? They are all external without any child nodes. And this will be the level for h, right? So d equals h, the maximum depth. And what about the number of nodes? The number of nodes will just be equal to 2 to the h, right? Just that level. So what we are really considering is, in the minimum case, only a single node right here. In the maximum case, we actually got everything at the bottom here, the maximum we can get. But in both cases, the tree is of height h in both cases, right? In this case, height will be h. In this case, height will also be h. But you can see the shape of the tree is very different. So that's why you see 2 to the h as a maximum, right, for external. All right, any question? If you somehow you grasp about the number of nodes and also heights from last time, I think this one definitely is not difficult. It's very similar, right? You just have to understand how to draw the tree accordingly and also see the analysis. Okay. All right, let's now move on. How about internal nodes? Basically the same diagram, basically. But the calculation will have to be adjusted accordingly. Okay? If you simply consider these two shapes, let's say this shape over here and this shape over here, somehow the minimum and maximum for internal and external share the same cases. So this case, we got a minimum external node being here. And the minimum internal would just be right here, as opposed to the maximum being all the nodes from level 0 all the way to level h minus 1. Right? They kind of share. Okay? So the case for minimum of the case of the minimum for external and internal are just the same. You just got to calculate different parts of the tree. And similarly for maximum. All right, let's now draw that very quickly, okay, and see. So we still got this example here for h equals 3. And we can still do that one like a slanted tree. So we got the root 1, 2, and 3. And this time, what we have to identify is not the bottom node here, because now we talk about internal. So the nodes will be the rest. 1 here, 1 here, and 1 here. All right? And it's basically about, let me just draw one more thing here. So here we got h is equal to 3, right? That's the example we are talking about. How many internal nodes exactly? H minus 1, right? Oh, sorry, just h, beg your pardon. The h is 1, 2, and 3, which correspond to exactly 1, 2, and 3 internal nodes. So just the same. So that's why you will see h is a lower bound, not h minus 1, beg your pardon. Okay. What about in general? In general, very similar diagram, so we're just going to draw. Let's say we got a root over here, and then we go all the way to here and here. And we have to identify all the internal nodes from the root all the way to the last internal nodes right here, right? If you think about here, the height is equal to h. The number of internal node will just be h, similar, right? We kind of verify that in this example here. So the number of internal nodes will just be equal to the maximum number of edges, just the same, which is equal to h. For maximum, similar. We're going to draw the case for maximum external nodes. That case will just be the case for maximum internal nodes, the same. You're just going to calculate the different parts. So we got h here equals 3, so I can start. So level 1, level 2, and then level 3. And now for internal nodes, it should be everything except for the last level, right? I'm just going to do, let's say, internal. So 1, okay, let me do a little bit better. 1, 2, 3, 4, 5, 6, 7. Okay, 7 exactly. Okay, and we can just verify. Okay, how many nodes in total in here? Let's apply the geometrical sequence just to see the general pattern. But here, of course, you can just count. But that's just an example. So you can say 2 to the 0 plus 2 to the 1 plus 2 to the 2, right? Level 0, level 1, level 2, which will be, if you remember, sk will be 2 to the k minus 1, right? Number of turns. We got 3 turns here, obviously. So 2 to the 3 minus 1, which will be 7. So 7 is exactly what we got here, right? I think it's also a nice review, right, for what you're going to be tested on Thursday. All right, what about general? In general, we're just going to draw the tree with the height h. In general, we're going to get a full binary tree. Oh, in the general case, will be a little bit interesting to consider. Okay, let me put it here. In general, I'm going to put it here. Okay, the height will be h. All right. Let me split this tree here of height h into 2 parts. And then I'm going to speak about exactly how the tree can look like. We have some flexibility over here. But the upper bound is just going to be 2 to the h minus 1. It's going to be the same. Okay? You want to think about, we got the bottom level here. This is the bottom level, which has some flexibility, which I'll speak about. But let's look at what's above. So from level 0 all the way to level h minus 1. This part here is more like a, I wouldn't say a subtree, but it's more like a subtree visually, not the subtree that we define, right? So think about this tree here, just this part, just this one here. This tree here is basically a full binary tree of height h minus 1. So this is a full binary tree of heights h minus 1. Okay? This will be the maximum case when you can get all the internal nodes covered in that particular region, right? What I tried to box over here. Now, at the bottom level, how many nodes do we have? We got to be careful here, right? You're going to think about what should you put here. But let me talk about it a little bit later. If I already got a full binary tree of height h minus 1, all the nodes here will be internal nodes. All the nodes here. Okay? So we're going to say all nodes here are internal. Okay? That means we're going to have the following sequence. We're going to get 2 to the 0, 2 to the 1, plus all the way to, because the height is h minus 1. Right? Let's add up all the way to h minus 1 level. 2 to the h minus 1. Right? And then let's apply the formula very quickly. How many turns do we have? We got 0 all the way to h minus 1. H turns. Right? Should be 2 to the h minus 1. All right? Let's get it out of the way because this one here simply corresponds to the upper bound you just saw over here. All right? That's how you visualize that. But let me talk about the bottom level here. That's kind of interesting. For the bottom level over here, you want to think about, does the whole tree need to be exactly full binary tree, meaning that we got to get a maximum number of nodes in order to get the maximum number of internal nodes right here? That's a question. Okay, I'll put it down, and then I'll give you the answer you can think about. Does this tree of height h, right, need to be completely full? Okay, I can definitely write better over here. F-U-L-L. Okay, it's a yes or no question. Okay, does it need to be full? If it has to be full, that means we're saying that the number of nodes here should be completely filled out, which is 2 to the h. It turns out it doesn't need to be, all right? Because all we got to make sure is, at this level here, we want to make sure our answer here is not compromised. As long as we can be sure all the nodes here at h minus 1 are still internal, we'll be fine, right? So now what we can think about is, one example would be, so we can say the answer is no. Okay, first of all, no. Doesn't need to be. I'll put the hints over here, which you can think about. As long as each node at level h minus 1 has at least one child. It is okay. So what do I mean by that? So for example, let's say I got one node here. That one there has just one child. Can be a left child. I have a node over here. That one there has maybe a right child. Doesn't really matter. As long as all the nodes at the level h minus 1, they are not external. In which case, whatever you have calculated will not be compromised. So that's my point. All right? So this is a little bit deeper question that you guys want to look into. All right? All right, any question about this? Yeah, take some time to digest, right? The bright side, this part here is not going to be covered on Thursday, but you definitely want to dive into it and think about these properties, right? Okay. So now we are done with the mathematical properties about binary tree in general. We talk about number of nodes, the heights, and also internal nodes, external nodes. And I would like to do over here some nice proof together with you that can give you more insight about how you can think about trees abstractly in general. Okay, let's do that. It's a very beautiful proof that we're going to see. Okay, so what we just covered were the slide number 33 and slide number 34. Okay, let's now define one more terminology, which is called proper binary tree. Once we have defined that, which is very easy, we're going to prove some mathematical property about it using mathematical induction. A binary tree is proper binary tree if each internal node has exactly 2 children. Exactly 2. Okay? Either the node is external, in which case has 0 child. If if the node has more than 0 child, it got to be 2. That's what it is saying. This is one example. Okay, let me show you why that example there is a proper binary tree. You can see what are the internal nodes. This is internal, 2 children. This is internal, 2 children. This is also internal, 2 children, right? Internal, 2 children. And also internal, 2 children. For external, that's okay. They just got 0 child by default. If I simply remove this particular branch, then that will not be a proper binary tree anymore. Because this node here is internal, but it has only 1 child, but not 2. So it's not proper. That's a definition for proper binary tree. And let's now move on to proving some nice property about proper binary tree. Okay, as you will see from the slides, the property we want to prove is the following. Okay, I'll just go over the property here first. Okay, it's there. So given that a binary tree is actually non-empty, you got at least one node. Okay, cannot be empty tree. And also the binary tree is proper. Each internal node has exactly 2 child nodes. If we got these 2 assumptions, and then we're going to use some notation here. So we have here we got n with a subscript I, and also we got n with subscript e. And here we got ni is the number of internal nodes in that particular tree. And ne is the number of external nodes in that particular proper binary tree, right? We're going to use these 2 notation, right? And this property here always holds. The number of external nodes will be equal to the number of internal nodes plus 1. All right? Let's see. Let's verify that very quickly, okay? Why don't we try the following? So let me say, let's count the number of internal nodes first. 1, 2, 3, 4, 5. Versus 1, 2, 3, 4, 5, 6. Right? 5 versus 6. Number of external nodes is 6. Number of internal nodes is 5 plus 1. So this works on this particular example. But that's not how you prove it. You got to prove it by something way more general. And we're going to use mathematical induction. All right? Specifically, we're going to use the weak induction. Okay? But don't worry about the weak versus strong. Right? That one I wouldn't worry too much. I'm going to walk you through the steps about mathematical induction. This may not be, of course, this wouldn't be covered in the written test, but in the exam, it could be that I give you another kind of property applicable to some binary tree of a particular kind, and I want you to prove it. Then you may want to see the structure over here to see how you can reproduce this kind of pattern for mathematical induction. Given that the tree structure here is recursive, it's very natural to really argue about its property using mathematical induction. Because the way you actually go with mathematical induction is you got to think about inductive hypothesis. That one there is really about recursion, okay, if you think about it. Okay? But I'm going to go over steps with you. Well, to start with, let's talk about base case. Since we know it's not empty, so what's the base case? When you got only one node in the tree, right? So let's start with the base case. And for the base case, we already want to argue that this little equation here is going to hold. So for the base case, we have a singleton tree. Singleton proper binary tree. Let's visualize that. Just one node. Is that node external or internal? External, right? Has no child nodes. In that case, the number of external nodes is exactly 1. And the number of internal nodes is 0. And this one here holds. 1 equals 0 plus 1. So base case is okay. So we're good. All right. And here I can simply say the property holds. And we got to think about a recursive case. To think about recursive case, let's make the inductive hypothesis first, and I'll make it a little more general for you. Okay? So I'm going to write down the inductive hypothesis, which we assume on some smaller input, and then we're going to use that inductive hypothesis to grow the tree just by a little, to really make sure it also holds on a strictly larger input. And then that's how we prove inductively. So let's write down the inductive hypothesis. Okay? So inductive hypothesis. Okay, I'm just going to use IH, which I'm going to refer to a little bit later. Okay, inductive hypothesis. And I want to make sure all the trees, any tree that is not singleton, is going to satisfy this property. That's what I'm going to assume. Okay. So we say that for a proper binary tree of size larger than 1. As long as it has at least 2 nodes, then that's something I'm covering. Okay? Larger than 1. And then I have this particular property satisfied. I got the number of external nodes equals the number of internal nodes plus 1. I assume that. Okay. Okay. And then, so this would be internal, and this would be external, right? And I'm going to use that very soon. And let's think about given a tree like this, let's say. Let's see here, given a proper binary tree, something you're given. Let's say I'm going to draw it very abstractly. Let's say this tree over here is a proper binary tree. Okay, this one here. And then I want to somehow show that, oh, by the way, this one here is where the inductive hypothesis will hold, which I'm going to apply a little bit later. Now, I want to show that if I can somehow grow this particular proper binary tree just by a little, to the minimum extent possible, if that extended proper binary tree can still hold this property here, I'm done, right? That's what I'm going to do. But how do I grow that? For example, let's say this is a proper binary tree. How can I grow that by the smallest extent? One way to do that would be, I can say, I can choose one of the external nodes right here. I can choose that one there. Let's say we choose the rightmost external nodes. And then I'm just going to expand that into an internal nodes, like that. By the way, I cannot just add one child to that particular external node. How come? Because the result is not proper anymore. There's only one child, right? So the smallest extent I can really introduce for extension will be add 2 nodes as child nodes for some external node. And let's say we just want to choose the rightmost one. All right? So let's say if I got some nodes over here that's already currently external. Okay, so this one here is really external. Okay, and then I'm going to do some change there just in general. Let me write it down textually, and then we'll talk about it. So here I'm going to say extended by the rightmost external node. Let's give it a name. Let's say n. So I'm talking about this node here. I call it n. The way to extend it is I want to introduce 2 child nodes for that. So n will become internal. Okay. By choosing the rightmost external node n and adding 2 child nodes to it. Let's say x and y. Let's say, all right? So what I'm doing here is I've chosen this n here, and then I'm going to add 2 nodes here as child node. One here, and also one here. X and y. All right? Abstractly, hopefully that makes sense, right? We just want to grow the tree. Okay? And let me just make some space for myself. Okay, let me just maybe make this one much smaller. You kind of get an idea already. Now here comes the important part. We want to see exactly how we can work out the numbers about external and internal before and after the extension. Okay, just bear with me. I'm just going to make this one much smaller, right? Okay, right there. I'm going to, remember we talked about ni and also ne, right? So now I'm going to introduce 2 more notation here, okay? You can think about the Ni and Ne. So these two are before the extension. Before the extension. And the extension is really by choosing the rightmost external node, right, and grow it. That's the extension I'm talking about. And what about after the extension? After the extension, I'm going to call that Ni prime. Ni prime somehow maybe increased or decreased. We got to work it out. Okay? And also, we're going to call that Ne prime as well. And this will be after the extension. Okay? So these two are after the extension. All right. Let's now talk about it. All right. So we want to say two things. Let's start with maybe Ne prime. The number of external nodes after the extension. How would that change? Basically, you can think about everything except the n, x, and y are really the same as before. So all we got to focus on will be exactly this part here. That's the only change we're making, right? But I got to be very precise. How is the external going to change? Before the extension, this one used to be the external node. But after the extension, it's no longer the external node. So we minus 1, first of all, right? So it's going to be the Ne before the extension minus 1. And this minus 1 here is really about the n being turned from external into internal. That's minus 1. What about, are there any other external being introduced? Yes. X and Y are the new ones. Right? So these are the two. That's new. So I'm going to say plus 2. And the plus 2 over here are really talking about X and Y. So this proof here really trains you to be very cautious about counting what's really exactly the changes, right? And let's now simplify that. It's going to be exactly Ne plus 1. Agree? Okay. So we're saying that after the extension, the number of external nodes will be before the extension plus 1. And that's the detail justification. All right? And we do something similar for number of internal nodes after extension. Something similar. So what we do is the number of internal nodes prime equal to, okay? And this one is actually not too bad because before the extension, n here is external. So that one doesn't really change. But now since we're adding these two, so we can just count them, right? So now, oh, sorry, let me say it again. Before the extension, n was external. But after the extension, it has become internal. And these two are just external. So we only added this one single internal node into the tree. All right? So all you got to say is, you got to say Ni plus 1. And this plus 1 over here is really the node that we have converted. So if you think about minus 1 and plus 1, that makes sense because n that used to be external is now internal. So that's why minus 1 versus plus 1. And for x, y, they are external, so they are not relevant here. All right. Let's now call these two some equation number, and then we are almost done in the. We're done with this this step. One more step. I'm going to name this one step equation 1, equation 2. All right. So what's really left for us to really finish the mathematical induction? We haven't even used the inductive hypothesis just yet, so we are not done yet. Okay. So what we want to really show. What we really want to show is that this particular property here should still hold after the extension, meaning that n e prime equals n I prime plus 1. This is something we would like to show, but we haven't seen that yet. In order to show that, we will have to use equation 1, equation 2, and also inductive hypothesis. Right? That's going to complete the proof. Okay, final step, which I'm going to write right here. Final step right here. So for the final step, I'm going to start with NE prime after the extension. The number of external nodes will be by equation 1. I know that NE prime equals NE plus 1. And now, since I go back to the before extension phase, I can definitely use the inductive hypothesis. I know that NE is simply Ni plus 1. All right? So I can use the inductive hypothesis over here. So Ne is simply equal to Ni plus 1. So Ni plus 1 and then plus 1. All right? Which will be, and if you look at this part here, Ni plus 1 is exactly Ni prime, right? So I can use equation 2 over here. I can just replace just this part over here. This part over here is exactly Ni prime. So what have I got? I got right here, Ne prime is equal to Ni prime plus 1. Right? I basically have shown after the extension, the number of external nodes is exactly the number of internal nodes after extension plus 1. All right? Quick recap. Step number 1, you want to show base case. Step number 2, you state the inductive hypothesis. Step number 3, you want to think about some strictly larger tree structure there by showing some extension. And then you'll work out maybe some equation over here. And then step number 4 is you want to do the final justification to really say that after the extension, this formula here is still going to hold, except you're going to replace Ne by Ne prime and replace Ni by Ni prime. All right, so that's the final outcome. It will take some time to digest. So what I suggest, the way you study for this is, number 1, understand exactly what's the property you're trying to prove. Number 2, really try to look at each step we are doing, because the property you might be given later could be a different property, but the structure will be very similar. Okay? Yeah, question?
On the slides, it says Ne prime equals Ne prime plus 1. So I think there's a mistake there.
Could be a mistake on the side. I'll double check later after class. Thank you. Yeah, as a fellow student pointed out, there could be some typo on the slide. I'll double check after the class. Yeah. If there is, I'll update that. All right, guys, any question about this proof, just in general? Of course, you got to take some time, right, to really understand that. I wouldn't expect maybe 2D question right now, but it will take some time. We're good? Okay. All right, so let me do very quick 2 more things, and then I think we're done with this particular tree lecture, and then we'll take a short break. Okay, just 2 more things, very quick. All right, so we are done with this proof over here on the slide number 36, but as your fellow student pointed out, I'm going to recheck the equation here, and then I'll reach out to you if there's any typo. Okay, binary tree application, basically something called decision tree. Very easy to go over. You just talk about each internal node is more like a question. And for each question, the answer could be either yes or no. That's why it's a binary tree, branching out 2 times only. So it's a proper binary tree. It's either yes or no. There's no ambiguity between the answers, right? So that's one application. Another application here is really about the expression, arithmetic expression, right? So that one there, I'm just going to show to you. And that one is very typical CS or self-engineering problem. You're given some expression tree, and then you may want to, for example, evaluate it by traversing it. And if the tree is in order, the typical traversal order you will go for is the in order traversal, which I'll show to you. All right. So the principle for expression tree like this is for external nodes, i.e., you got external nodes right here. 3, 1, 3, 9, 5, 2, 3, 7, 4, 6. So these are the external nodes. So these are all the numerical constants. Numerical constants. And also you got others, internal nodes. You got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, just 9 internal nodes. All the internal nodes somehow represent some operator or some operation you have to perform. For example, if I'm talking about this particular subtree, I'm talking about 3 plus 1. If I'm looking at this subtree over here, I'm talking about 3 plus 1 first, and then multiply 3, and etc. All right? So that's about internal nodes. And for the internal nodes, so these are just the binary numerical operators. Numerical operators. Okay. So that's another typical usage for a binary tree. And apparently, this tree over here is proper. Agree? Because all the internal nodes, they simply got exactly 2 children. Right? Now the question is, if you want to represent arithmetic expression in general, does it have to be a proper binary tree? That's a question for you. Should it or should it not? Yeah?
It should be, because in order to perform an expression, we need 2
2. Okay, you're saying, okay, you kind of hinted the answer. You're saying in order to perform an operation, you should need both operands, right? Is it possible to have an operator that needs only one operand?
I guess like
Exponential in some way, yes. How about negative? You can think about if I say negative 5, I'm really saying I'm taking 5 and apply -1 to it, right? So the answer is not necessarily in general. For example, let's say if I got -5, let's say multiply by 4. It's a valid arithmetic expression. In that way, how do I express that? I can say multiply, which got 4 here, and that one there just got minus, which has 5 here. So this one is really saying this subtree over here is talking about this expression. This subtree here is real. Oh, sorry, let me do a little bit better. This subtree here is -5. And this subtree over here is just about 4. And if you look at this, what this subtree is representing is, you want to say multiply, and then with both expression. So you have -5 multiplied by 4. So not necessarily proper, okay? Not necessarily. Sometimes you might even got like a ternary operator in Java, right? In which case, you might have a general tree, which is okay. Okay, it really depends on what you need. All right, let me do one more thing, and then we'll take a very short break. Okay, I want to do in order traversal very quickly. And if you go back to the slides, that will be the last thing I want to talk about. So if you look at traversal, we already did pre-order and also post-order. And guys, one more reminder, right? This will be applicable for Thursday. For pre-order and post-order, it can be on any tree with any number of children. But for in-order, you cannot do in-order traversal on a general tree with more than 2 child nodes. You cannot do that. There's no such definition. For in-order traversal, definition is you got to go for, basically, if there's a left child, you're going to go for the left subtree recursively, and then visit the parents, and then go for the right subtree and go there. Right? So that's the order. That's why it's called in order. All right, let's now do one more example here, and then we finish off what we left last time. Okay, this one here is actually quite straightforward. Okay, I'm going to put it down here. Okay, right here. Okay, I'm going to get 3 plus 1 multiplied by 3 divided by 9 minus 5 plus 2. And what I have completed is the in-order traversal for just this particular left subtree. Once I've done that, I'm going to put a minus, which corresponds to the root. So now I have done recursively the in-order traversal on the left subtree, and then the root. What I need to do now is to do the in-order traversal on the right subtree. Okay, that one there is going to be 3 multiplied by 7 minus 4 plus 6. All right. I'm just following the algorithm that's on the slides. I'm just doing a little bit quicker. right? So what you got to do is you got to make sure you go with the same example here. You can feel free to modify the tree yourself and see what the pre-order, in-order, and post-order traversal should be. Of course, feel free to put that into Java, right? That's going to tell you the answer. Okay. All right, any question here? All right, why don't we say we take a 2 minutes break and then we'll do binary search after the break, okay? All right, we are basically done with the general tree lecture. So we're done with everything, but for your written test, I already confirmed the coverage. You can confirm with that, but everything's done. For the general tree, binary tree, now you definitely got some basics about a tree. So we're gonna divert a little bit right now for maybe maybe 2 classes, hopefully. I'm gonna talk about a little bit more about recursion, especially how we can do some sorting and searching. So these 2 are very fundamental problems that we're gonna need to know. And then after the diversion for about 2 classes, hopefully, maximum, and then we're gonna go back to some more advanced tree that we're gonna have to worry about. Okay, we'll get there. So we are done with this lecture here. And you can also check the lecture slide on the lecture site, recursion part 2. Okay, so I'm gonna talk about 3 algorithms. For today, I wanna do, I'm not sure if I can finish, I'll try. If not, we'll definitely at least finish the most part about binary search. We're going to talk about recursive algorithm and binary search first. And then we're going to talk about next week merge sort and quick sort. Right? I kind of mentioned them in the beginning of the course, but we're going to see exactly how they can be done. I also got the working code in Java already on the lecture side. If you want to do some preview, some pre-study, you can feel free. But let's talk about binary search today. And I'm going to be mostly using my iPad. I want to talk about what's the intuitive idea about binary search. That's very important. And today I'm going to focus on doing binary search on a linear data structure. It could be a linked list or it could be array. Let's say array or array list. Let's say array. And then once we learn about the basic today, I'm going to connect what we learned today into when we got a tree structure. How can a binary search also be applied? Right? That's something we got to learn as well later. Okay, it's a searching problem. So it's a very, if you want to do binary search, it is important for you to know this precondition. Okay, the array that you're given as input must be sorted. If the array is not sorted, you cannot do binary search. Let's talk about what if it's not sorted. If it is not sorted, you basically go back to your 1022 or 1021. How can you search through an array to see if some element exists? We know exactly how to do that, right? But that one there is going to be linear time, because you might have to search from the beginning all the way until the end, linear time. But for binary search, if you can get this precondition satisfied to get the array sorted beforehand, then this particular search is going to take, I can tell you right away, it's going to be log n. It's going to be a drastic improvement. We got n improved to log n. But now we're going to tell the whole story. We're going to talk about the idea about binary search, and then we're going to look at some Java code, recursive version, of course. And then we're going to look at how we can figure out the asymptotic upper bound for binary search. And the technique I'm going to show to you is something called unwinding or unfolding. That's something we're going to do. Okay, one step at a time. Let's talk about some idea for binary search. And guys, don't forget, the precondition for you to do binary search is the input array must be sorted. Must be. All right. And let me talk about some real life example. I'm not too sure if you guys are still using hard copy dictionary. Have you even heard of it? Oh my goodness. Okay. So I do have some dictionary in my office. If you're curious to see what it looks like, feel free to come by. Well, just, yeah. Well, it's too bad, you know. It's a nice experience. How about I just describe it? You can imagine what a dictionary is, okay? I know these days you just search. But I can tell you that whenever you want to search what the English word really means, behind the scene, most likely they're doing binary search. Right? Anyway, so imagine that you have a dictionary, like a book, right? From page 1 to page 1000. Okay? So think about the book, looks something like this. Okay, so this is some dictionary. And the way the pages are ordered is sorted alphabetically. It's going to go from letter A all the way to the letter Z. Right? It's going to sort in this way. For example, I might get, I don't know, So I may get, for example, apple, for example. This might be some word over here. And then this will be, for example, there may be something called Z. Sorry, just coming. I don't have any word in my mind. Okay? Huh?
Zebra.
Okay, sure, whatever, right? So you kind of see the idea. You want to somehow sort all the English words in the dictionary by their alphabetical order, right? That's the principle. Okay? Now, let's use some word as an example. Let's say I want to search the word Oxford, for example. It's O. It starts with O. So what I typically do with the dictionary is I simply turn the dictionary into half page, half of the book. So if I go to the half, it's going to be maybe about letter K. Right? Let's say I'm there. I'm not there yet because Oxford should be O, right? Now I want to think about, should O appear after K or before K? Should it be after K or before K? After, right? Right? Agree? Okay. So that means if I turn to the page to the K, if Oxford does exist in the dictionary, it must be in this particular half. Now I can safely disregard this particular half from A to K. This is a very critical step for binary search. For binary search, given that the input you're given, for example, array or dictionary, is actually sorted, if you know where you are in the middle, you can now judge to see whether you should go to the left or you want to go to the right. If you decide to go to either side, you will know that dropping the other side is safe. You're not going to miss anything. That's a critical insight into binary search. Okay, continue a little bit. And I know that if Oxford does exist in the dictionary, it must be over here. It must be. And then I will turn this remaining pages in the book into half again. So I can say I want to go to, let's say, W. Okay, let's say I turn into half, it's somehow W. So now, should I go to the page before or after, right? You want to think about if O here should go before W or should it go after W? Before, right? So that means what I should do is I should really go to this part of the dictionary. By going to that part, I'm basically disregarding this part over here, right? I'm going to keep doing this half and half until I see that word. That's how a dictionary works. All right. I think in the old days, they do have something called the dictionary competition, where they give you some very complicated word to see how quickly you can find that word in the dictionary. Right? Of course, you wouldn't have seen that. Right? All right, so that's like an example here. And let's now try to make it a little bit more relevant to programming. Okay? But you can more or less see how it works intuitively. You just have to somehow decide to go to the middle point and then to see which half you should really go and keep doing it until you find the thing. Or until you have nothing else to search for and then you know that the thing you're searching for doesn't exist. Right? All right, so let's now talk about the binary search. Okay. Oh, let me say one more thing. There is a term called search space. In the beginning, I'm searching through the entire dictionary. Once I turn into K, I reduce my search space into just half. Once I turn into the page for W, I can narrow my search space to another half, 1/4 basically. Right? I can keep narrowing the search space. Let's think about how the search space size is going to change. Let's think about it. Okay. So I'm just going to put something here. So the size of the search space. Right? That's what I want to work on. In the beginning, it's the entire dictionary. Let's say the dictionary got n entries. Right? And when I turn into about halfway, I'm turning to halfway, and I decide that the word I'm looking for should be right here. So what about this new search space? It should be n over 2, right? And then it's going to drop to n over 2 after the first search. And then I can also go to another one here. That one there is going to be n over 2 divided by 2. N over 4, right? Keep going. The idea is you want to really keep shrinking down this search space until ideally, you get to just one entry and check to see whether that entry is really what you're looking for, ideally. Okay? So we basically got n here, n over 2, n over 4, all the way to hopefully eventually 1. Of course, if you can search that word, if you can find that word earlier, you just return, right? This is about how many searches you will need. The number of comparison. Because every time, if I'm here, I'm comparing K against maybe O, for example. And here, I'm comparing W against O, right? I'm going to keep comparing. How many comparisons do we have? You got to think about how many times it will take you from n all the way down to 1. Each time, you just divide the search space by 2. All right? It turns out this is log n. But we're going to see exactly. I'm just giving you the result, first of all. All right? It's going to be log n. This tells you that in the worst case for binary search, it will only take you log n times of comparing the value against the dictionary to get to the target word, maximum. It might be less than log n, but maximum log n. So this is way better than a linear search. All right? Let's now take a look at the array example here. Let's do one more thing, one more time, okay? Let's make it more relevant to programming. So when I show you the Java code, you will see that more clearly, okay? Let's say you're given this particular input array that's assumed to be sorted. The first step is you want to find a middle point, pretty much like finding the K over here, okay? To really calculate this middle point, it can be just a.length minus 1 divided by 2, right? You calculate what's the middle index. Sometimes we may not divide evenly, in which case you can take the ceiling or the floor, right? You can do some adjustment. But let's say you can divide properly. So you want to think about this one here is what we call the middle value. So this one here is some middle value, V. And this one here, that what we compute is the middle index. Every time you go to a new search space, you have to recalculate the middle value and the middle index. But the calculation themselves are primitive operations, right? Okay, so let's say this part here is really the middle value over here. What you got to do is, let's say we're searching for the value K. We're searching to see whether K exists in the entire sorted array. The step number 1, calculate where the middle is. Compare V against K. So there are 3 cases. If K is exactly equal to V, we are done. We found it. However, if K somehow is less than V, given that it's sorted, oh, by the way, non-descending, right? We talked about it earlier, right? So if I could remind you visually, non-descending simply means it can be maybe ascending, or it can be flat, can be ascending, right? That's all we spoke about earlier. Okay. So if K, let me just write it down first. Number 1, you have to keep accessing the middle of the search space. Okay? And the way you try to get a search space, you gotta get a half search space each time. It is halved each time. When you are given this initial input, the entire array is the search space. So that's something I'm just going to write down for the first time. So you can think about this entire array right here is the initial search space. Initial search space of size n. All right. Once we get that initial search space, we want to halve it. Now, which half should we go? We can either go to this half or we can go to this half, right? We're going to decide. So you're going to look at the value K here, compare that against V. Right? So that will be the second step. It's going to be recursive. You got to keep doing it. So you're going to recur make some recursive call on, so there are two cases. I would say A here and also B here. Okay? You will recur to the left if something. You'll recur to the right if something. Right? We're going to fill out a condition pretty soon. So let's talk about, let's say, if, what does it really mean when you want to recur to the left? If you want to recur to the left, that means you're going this way. So this will be the new search space. If this is a new search space, we know that all the values over there will be strictly less, will be less than or equal to v. We only go there if k also happen to be less than or equal to v. So there's a chance k might be there. All right. So this will be if k is k less than or equal to v might be in this half. Because odd values here is guaranteed to be less than or equal to v, because we know that the array is sorted. So this insight here is very important, right? So you have to compare the value you're searching for against the middle value. If the middle value is not exactly equal to k, you got to go to either left or right. So if k happen to be less than or equal to v, there is a chance it might be here, because all the values over here in this half is guaranteed to be less than or equal to v, given that the array is sorted, right? So these kind of the logical argument there. Okay, so you go to the left if k is less than or equal to v. Okay, and then or you can say less than, because that's equal to, of course, you found it. Okay, less than v. All right. And symmetrically, you will go to the right if k is larger than v. If k is larger than v, then k might be here, because the guarantee all the values in this right half is larger than or equal to v, right? Because the array is sorted. Okay. Okay, I'm gonna just write this half over here, so that will be where it might go. Okay, if you go that way, so this will be k larger than v. Okay, so let me just fix that inequality here. I should really say less than. Again, I don't say equal here, because that's equal to v. We have found it. We don't need to go any further. Okay, might be here. Because all values here larger than or equal to v, because it's sorted in the non-descending order. All right. Right, it's just about the idea, right? If you guys kind of get some idea here, and then we can see Java code. We're going to follow this idea very closely, right? Once we go to Java code. Any question? All right, so let's now take a look at the Java code. And maybe we can do some tracing. We'll see. Okay, so the Java code goes like this. It's recursive. You can see we have some public method here. Binary search is going to call binary search helper. And the binary search helper is recursive. Let's see where the recursive call is made. So binary search is here. So we make one recursive call, and there's another recursive call. And notice one thing right away. You can see the context for making this is under if. The context of this is else if. That means these two recursive calls cannot happen at the same time. We go either one, but not both. All right? That's also very important insight. Okay? So these are the only two recursive calls we're going to make, and somehow the condition here correspond to what I said earlier about less than and also greater than. Okay? Let's dive a little bit deeper, and then we might do some tracing. Okay? And this actually goes back to about the array recursion that we spoke about in the beginning of the semester. Okay? So we get some array input here that's sorted. Okay? And then we simply go from 0 to sorted minus 1. Okay? You can see 0, and then the length of the sorted array minus 1, right? Go from the beginning until the end. And what we're looking for is this particular key. We're looking for it, right? And then we got two base cases over here. The first base case would be if from is larger than 2. That's about empty range we're specifying, right? If the array is simply empty, or the search space is empty, we have not found it. So we return false. And if the from is equal to 2, that means now the search space is exactly one element there. In that case, we simply compare if the key has been found. If it is not, then return false. If it is, return true. Okay. So you can see the key here is what we are comparing. All right, so these are the two base cases. Either when the search space is empty or it's not just one. And the else part here is the recursive case that we have to dive a little bit deeper. Right? So this part here is the recursive case. Recursive cases. Okay. By the way, the else part over here is about when the key is neither less than nor greater than. That means k is exactly equal to the middle value. In that case, we have found it. Okay. So I can talk about that case right away. This is the case where the k value we are trying to find exactly equal to the middle value. Exactly equal to that. So just return true. Okay? And notice that we're calculating two things. We're calculating the middle index, which is from plus 2 divided by 2, right? That one pretty much corresponds to what we said earlier about calculating this middle index. That's exactly what we're doing. Okay? And that one there is going to be, so you can think about the middle is the index here. And then we got also middle value is whatever that's stored right here. So I'd say MV, middle value. Okay, that's the element here. And we got two possible recursive calls to make, either one but not both. When the key is less than the middle value, we know that it must exist over here. But let's now be more precise. What should be the new search space if we made a recursive call? The search space should be exactly here. Okay, right here. Because we know that the middle value is not exactly equal to the k we are looking for. But we know that key is less than middle value. Okay, so this is the case where the key is strictly less than the middle value. In that way, there is a chance it might be here. So we are making a recursive call here. You can see the same array called by value. And here, notice the difference over here. Key that we're looking for is still the same. It's just that this part here is different, right? So this part here you can see is from and then middle minus 1. From is still here, and the middle minus 1 is this value here. Middle minus 1, the index. So that's why I said this is a search space that we got to call on. All right? Symmetrically, if the key is not less than, then it could be greater than. In that case, we're just going to go for this part over here. So this will be the search space where we got the key strictly less than the middle value. But what exactly should be the new search space range? It's going to be, you can see the 2 here is just going to be here. Right? That one doesn't change. But we have to look at what's the index for the element right next to the middle, right to the right of middle. So that index will be the middle plus 1, right? So that's you see plus 1 here and also minus 1 here, right? That's a recursive call. So you can see the code structure here is not difficult. You just have to know exactly what each recursive call really means. Okay. All right, any question? We're good? Okay. I think now might be a good time to pause. Just give me maybe 1 minute. I will sum up very quickly before we continue next Tuesday. So for binary search, we're basically done with the basic idea, like how things will go, and also see the Java code. Next time, I'm going to finish off in the beginning on Tuesday about how to do some tracing for binary search. You can feel free to look at these two input over here and give it a try. And then we're going to talk about how we can formulate the running time for binary search, like recursive algorithm, using something called recurrence relation. And then we're going to work out some math together in the beginning. And then we'll move on to merge sort and quick sort. All right, thank you. And then I'll see you on Thursday.